Greetings. So, we are well into the discussion on quantum logic gates now, because we have learnt in the previous two classes how things developed from classical computers to quantum computers. We discussed what a qubit is, which is the basic unit which is used in quantum registers. Just like in classical registers you use the bits, and then you use different electronic gates which are basically made of symbolic logic, made up of Boolean algebra in terms of the zeros and ones in classical computing, right. And these will now be replaced by quantum logic gates. So, that is what I will introduce today. And the time of quantum computing has come, means until quite they are here, quantum computers are here, and your generation will be using quantum computers, coding and whatever algorithms you have to develop, they are going to have to be using quantum logic gates. It is not that you are going to dispense with classical computers, they will be required, they will certainly be necessary. They are not going to be replaced by quantum computers, but in addition to that you are going to have to use quantum computers. So, it is important to learn how the quantum logic gates work. So, the reason I say that quantum computers have come, you would have seen this picture. This is the IBM quantum computer which you can actually access. You can actually access this, you can sign in to get started. If you are new to the IBM experience, you can create an IBM ID account on this machine, all right, and start doing some basic operations so that you get your feet wet, and you have to learn how quantum computing is done. So, this is a nice machine. This has got two 5-qubit processors and a 16-qubit processor, and this is the competition from Google. And Google very recently claimed quantum supremacy, or sometimes it is also referred as quantum advantage or quantum eclipse. And there are these two industry giants, IBM and Google, they are contesting each other's claims and so on. So, the controversy is quite interesting, but what is important is that quantum computers are here. It is not that they are coming, and that is the reason you need to get acquainted with quantum logic gates and how to combine these logic gates to build quantum circuits, all right. So, whatever you did for classical computation, you build the Boolean algebra, the symbolic logic, and then using the 1-0 equivalence with switches being on and off, you carry over into this symbolic logic into electronic circuits using transistors, all right, and then using Karnaugh maps and so on, you build more involved circuits and then build digital electronic equipment and also classical computers. Classical in the sense that they are using, they are completely based on the binary bits 0 and 1, and not because they do not use quantum gadgets. Quantum gadgets, of course, quantum devices, quantum transistors are certainly used in all machines, but they are called as classical computers because they use classical symbolic logic based on Boolean algebra, the algebra of 0 and 1, and a switch is either on and off, a cat is either dead or alive in this scheme. So, quantum logic gates are reversible, and you know that qubits are represented by a matrix consisting of 2 rows and 1 column, right. So, it is a 2 by 1 matrix, and basically what are you doing in a gate? A gate is manipulating bits. So, now you are going to manipulate qubits, and if you operate on this matrix consisting of 2 rows and 1 column by a 2 by 2 matrix, you will be able to scramble the 0 and the 1, right. So, you carry out operations on this matrix, and these operators are represented by 2 by 2 matrices. So, a gate is that operator which will operate on a qubit and give you a new state. So, effectively what it is doing is to take you from one point on the block sphere to another point on the block sphere, from one qubit state to another qubit state. That is exactly what you want a gate to do, and you can represent this operation by operators which are represented by matrices which will operate on the qubit matrices. Okay? So, these matrices are unitary transformations. You know what a unitary transformation is. Okay? The inverse and adjoint are equal, and what these transformations do is to preserve the norm. You do not expect the norm to be changed, but you are the block sphere is of some radius, standard radius of unit 1. So, you remain on the same surface, you are not changing the radius of the block sphere. So, it remains normalized to unity, and that is what unitary transformations help you achieve. So, quantum logic gates will be represented by unitary matrices which preserve the norm of the state, but they will only take you from one point on the block sphere or the Poincare sphere to another point of the block sphere. Okay? So, these are rotations of the block sphere about some arbitrary axis essentially. So, that is what a quantum qubit gate does. So, we are initially going to talk about 1 qubit gates, and then we will of course get into 2 qubit gates, and then quantum computing involves multi-qubit gates. So, the quantum gate essentially manipulates the qubits and perform rotations of the block sphere about some axis, and let us see how this will be done. So, we represented a qubit as a superposition of 0 and 1. Okay? Now, this is completely non-classical, because in classical electronics you have only either 0 or 1. Here we have a superposition of 0 and 1. So, this is a quantum qubit, the qubit being represented by this 2 state, so 1 0 and 0 1. So, it is a linear superposition of 0 and 1. So, the vector 0 in the Hilbert space is represented by the matrix 1 0 and the vector 1 by 0 1. These are orthogonal matrices. Okay? And you can represent this, you can multiply the coefficients, right. So, now you have 2 matrices alpha 0 plus 0 alpha, you can add them up and get a matrix alpha 0 alpha 1. So, a quantum qubit is now represented by a matrix consisting of 2 rows and 1 column, and if you perform unitary transformations of this matrix, you will effectively be building a quantum gate. Okay? So, how to do it using physical objects is something that you differ. Now, that is something you did even when you built the classical logical gates, right. First you build the Boolean algebra, all right, and then start building the devices. So, here we are going to first find out how to transform these qubits using unitary transformations, first develop the mathematics of manipulating the qubits using unitary operators and unitary transformations of the qubits. So, we know that a 2 by 2 operator, 2 by 2 matrix will help you achieve this for a single qubit. So, subsequently you are going to have to use actual physical qubits. So, here are some examples of the 2 by 2 matrices. So, there is a quantum NOT gate. Okay? You are familiar with the NOT gate and classical digital electronics, right. So, it is going to do something similar, and this is actually called as a poly X gate or poly NOT gate as it is called. Then you have the poly Y gate and the poly Z gate. So, these are different gates and they will do different operations on a qubit and move it around on the block sphere to different points. Okay. There is another gate which is a very well known and a very widely used, which is called as the Hadamard Gate. It is named after the French mathematician, computer scientist Hadamard, and this is also a 2 by 2 unitary matrix, which is the 1 1 1 minus 1 and the scale by the 1 over root 2. And the reason they are called as poly gates is because the matrices that you are using are essentially the polymetrices. Okay? And the physics students amongst you will be quite familiar with the polymetrices, but the non-physics students may or may not have met them. But it's there is nothing mysterious about it. They are named after Wolfgang Pauli, who developed the spin quantum mechanics of spin half particles. And spin is essentially a quantum entity. There is no classical analog for this. So, you have two operators S square and Sz, which commute with each other, and the simultaneous eigenkets of these, because these two operators commute with each other, they allow simultaneous compatible observations, and these are the ones which are used to represent the polymetrices. Okay, the polymetrices are then developed in the eigenbasis of the spin half angular momentum operators. So these are the polymetrices, okay, the Sx, Sy, and there is an Sz as well. It's written over here, right. So, there is a Sz and Sy and Sx. This is the sum of Sx plus Isy, and this is Sx minus Isy. So, these are the spin matrices in quantum mechanics, and the matrices which I showed you, these are coming straight from the quantum mechanics of spin half angular momentum, and I have earlier lectures on atomic physics, the special topics and atomic physics, the NPTEL TL lectures, and you will find a fairly extensive discussion on the quantum mechanics of spin half particles and the angular momentum algebra of spin half particles. So, I will not repeat any part of it over here, but I will refer you to those lectures. So, you have a superposition of the vectors 0 and 1 in the Hilbert space, which represent the qubits. Okay? And what do you expect the quantum NOT gate to do? Quantum NOT gate, you would expect to move the qubit 0 to 1 and 1 to 0. Okay? That is what you are expected to do, and you are going to achieve it by rotating it about this qubit, which is a superposition of 0 and 1. Okay, this is the diagonal line at 45 degrees between these two, and if you flip this around this axis, you will be able to take the qubit 0 to the state 1 and the qubit 1 to the state 0. Okay. Now, these are the vectors in the Hilbert space, which is why I have drawn them as orthogonal. But then we are representing the qubits on a block sphere. So orthogonal qubits are represented by antipodal points. Okay, they are collinear. So now this is the plus state, which is at 45 degrees, right? And you have to carry out this transformation from 0 to 1 and 1 to 0. So you are going to do this on the block sphere now, right? So this is your block sphere, and these are your qubits, 0 and 1. 0 is at the north pole, 1 is at the south pole. These are orthogonal to each other. They appear to be collinear only because you're using this representation on the block sphere, right? And now you want to take 0 to 1 and 1 to 0, and you can achieve this by rotating this block sphere about the axis x, right? The flip represented in the Hilbert space about this axis, which is at 45 degrees in the first quadrant, would correspond to rotation of the block sphere about the x axis, right? So that is what you are going to do. So this is your block sphere, and you have a qubit which is your plus superscript, which is this plus superposition, okay? And you are going to rotate this hemisphere, this block sphere about this axis, so that the lower hemisphere goes at the top and the other one comes at the bottom, and that is the kind of rotation you are going to carry out. So the plus 1 qubit state, it is represented by theta equal to pi by 2, right? Theta goes from 0 to pi all the way, but this is halfway there. So theta is pi by 2 and phi is 0. So that is your state, and you have to carry out a rotation of the block sphere about the x axis, and this will give you the quantum NOT gate. Okay. So this is the quantum NOT gate. It is also the poly X gate because it is represented by the poly X matrix, and the poly X matrix is 0 1 1 0. So you can see very easily by carrying out this simple matrix multiplication that this will give you the NOT gate. Okay. So this is the quantum NOT gate. This is a rotation of the block sphere about the x axis, okay? And you have essentially carried out this rotation. So 0 comes here and 1 goes there, and you have rotated the entire block sphere about the x axis. So that's what the NOT gate has achieved, right? And if your qubit is a quantum spin system, it can be any two-state system, right? And the spin half are amongst the very popular qubits because they are a two-state system. So you get either spin half, which is up or down projections with reference to some axis of quantization. So you have got the up which goes to down and vice versa. So this is your single qubit NOT gate represented by the poly X matrix, right? What it does is to flip the spin up into the spin down and spin down into the spin up state, right? So that is the quantum NOT gate. So your qubit 0 is represented by 1 0, qubit 1 by 0 1, and essentially what you are doing is मरे को जिंदा कर देंगे और जिंदे को मरा कर देंगे, right? A qubit. So that's exactly what quantum mechanics can do, which there is no classical analog for this, right? So the quantum NOT gate, when it operates on the qubit 0, gives you the qubit 1, and when it operates on qubit 1, it gives you the qubit 0. And the matrix multiplication is a powerful tool and a very easy one to represent the quantum gates. So, quantum gates are going to be represented by unitary matrices, the 2 by 2 matrices, and we are acquainting ourselves with some of the basic quantum gates. So, if this is represented by the symbol over here. So, just like you have got symbols for classical digital electronic gates, there are symbols for quantum gates. So, this is the symbol for a quantum gate. You have got a certain input which is A00 plus A11. What is the output? It is A01 plus A10, because 0 is flipped to 1 and 1 is flipped to 0, right. So, that is the inversion which is achieved by the quantum NOT gate. So, this is the single qubit NOT gate. Now, there is another gate which is called as the square root gate. It is the square root of the single qubit NOT gate. So, it is sometimes called as a square root gate, and a NOT gate is represented by this NOT symbol, which is the same that you use in classical digital electronics, and then you have the square root of this, right. And this matrix is just the square root of this. Why is it a square root? Because if you multiply it to itself, you are going to get the Poly X matrix. So, you can check it out that when you multiply this by itself, you get the Poly X matrix. So, it is very appropriately called as the square root gate, the single qubit square root gate, and this is useful in analyzing the quantum flip. So, we are familiar with the classical flip. Okay. So, let me first remind you of the classical flip. So, if you have an initial state in which you have heads, then there is a 50% chance that you will get heads and 50% that you will get tails. Okay. So, obverse and reverse have exactly equal probabilities, it is completely random, right. And it does not depend on what your initial state was, it could be heads or tails. If your initial state was different, the final conclusion also remains equally uncertain. So, there is a 50% chance of getting heads and 50% chance of getting tails. So, this is what a classical coin would do, all right. So, this is called as a coin flip gate, and this is classical with 50% chance of success no matter what the initial state is, right. The result is completely random and it is great for generating random numbers. So, this is often used in random number generator, this kind of gates are used. But then we will also talk about the classical NOT gate, again a classical NOT gate, which is completely deterministic. So, whereas if you operate this by if you use the quantum flip gate, you get a completely random this thing. So, what you can do is you can generate a logic gate like this, which is the NOT gate, such that if you begin with heads, you will always get tails and vice versa. So, this becomes the classical NOT gate. Okay, it is completely deterministic. So, whatever was your input, you get just the output. So, this is the classical NOT gate. It has a deterministic output, right. So, if you start with heads, then you get tails and vice versa, and it does not matter whether your input is in terms of 0 and 1 or yes or no or up or down, you get just the opposite. So, it is a completely deterministic NOT gate. So now we introduce what is called as the quantum coin flip. So we had the classical coin flip is what we dealt with. What the quantum coin flip will do is, if it starts with a pure state like state 0, a qubit 0, it will randomize it. You will get a superposition of 0 and 1, both will be present. You start with 1, you will again get a superposition, but a different superposition which is orthogonal to the previous one. Okay? And this is what a quantum coin flip will achieve, and you can represent this by a unitary matrix, a 2 by 2 matrix, which you can see is this 1 over root 2, 1 minus 1, 1, 1. Okay? You can verify this very easily, because if you carry out this matrix multiplication, operate by the quantum coin flip gate on the qubit 0, 1, and ask yourself if you indeed get the linear superpositions that we just claimed. Can you see it quickly? Right? From the matrix multiplication, you can see immediately that that's exactly what you get. So this is what represents a quantum coin flip. So this is what is called as the quantum coin flip gate, and see how it is different from the classical coin flip gate, right? Now if you use the quantum coin flip gate again, so you are now operating by the square, what do you get? So you start with 0, 1, and you end up with 1, 0. But mind you, the 1 comes with a minus sign. Okay? But for a moment, if you ignore the minus sign, then recognize the fact that you started with 0, 1 and you are getting a 1, 0. So in some sense, it is a NOT gate. Okay? In some sense, it is a NOT gate. Nonetheless, there is a sign which can be of importance, because if you subject this qubit to any further, put it through further gates, then that minus sign is going to be very important. Okay? But at the moment, it plays the most important thing about this particular gate is to recognize that this is inverting 1, 0 to 0, 1. And in that sense, in the sense of inverting 1, 0 to 0, 1, it is a quantum NOT gate. Okay? And the matrix M, or the quantum coin flip gate itself, can therefore be called as the square root of the NOT gate. Okay? It is not very exact, because there is a minus sign which is coming here, mind you, but the term square root of the NOT gate is used, and this is very nicely discussed in a paper in American Scientist by Brian Hayes. So you will find it very easily, and this is called as the square root of the NOT gate, but there is a sign that you must remember. So some of these terms are used, but they are not to be taken literally. You have to understand the context in which these terms are used and what is the sense they are communicating. So this is the square root of the NOT gate. So you started with a pure state, and you get a superposition of the two pure states, the quantum qubit 0 and the qubit 1, right? So you have randomized it. But when you do it twice, you get 1 and 0, and this is completely deterministic. This is amazing. There is absolutely no classical analog for this. Okay? There is absolutely no classical analog, which is why it is a very counterintuitive gate. And what you are doing is you are passing a signal through a quantum coin flip gate, which randomizes it, right? And then you send it through another identical quantum coin flip gate, and what you get is a deterministic result. So, this article by Brian Hayes, he says that it is a machine which first scrambles eggs and then unscrambles the same, all right. So, there is no classical analog for this. So, this is the quantum coin flip gate. Then you have got the poly Y gate. What does the poly Y gate do? It acts on states alpha and beta, if you like, 1 0 and 0 1, and then it gives you 0 1 and 1 0, but then mind you there is a phase factor which is coming up because of this e to the I pi by 2, all right. So, it is like a NOT gate. From 0 1 you go to, oh, there is an I here. So, I is e to the I pi by 2, so that takes care of it, right. Okay, so we now look at what the poly Y gate does. Essentially what it is doing is it is carrying out a rotation about the y axis, but also multiplying by plus and minus I. So, that is the poly Y gate. Then we come to the poly Z gate, which is the poly which is represented by the poly Z matrix, which is 1 0 0 minus 1. What is it doing? It will rotate the Bloch sphere about the Z axis. So, it would seem as if the dots which represent the states, they remain at the same place, but the reference x axis and the y axis is going to turn, and that is the reason it picks up a phase, because now you have rotated this about the z axis. Okay. So, as a result of this, there is a minus sign when you operate on the state beta, which is a 0 1. Okay. So, this is the poly Z gate. So, now you have a fair idea of what the quantum gates are. So, basically you see that they are manipulating the quantum qubits, they are moving them around on the Bloch sphere, and depending on what kind of operation you are, what is the end result you want, you are going to use an appropriate quantum gate or combinations thereof, as you would do in digital electronics also. So, the Hadamard gate is again one of the important ones. It is again a 1 qubit gate, and it corresponds to quantum Fourier transform in some sense, but we will use some simple applications of the Hadamard gate just to get used to it. So, it looks a little bit like the square root of the NOT gate, but notice that the positions of the minus sign are different. Okay. So, we have already used the square root of the NOT gate in the previous discussion. So, it has a similar look to some extent, but the position of the minus sign is different. So, this is a different, so do not be confused with the previous impression. This is the Hadamard gate. It is represented by this letter H in the box, and if the Hadamard gate operates on a qubit, what you are going to get is represented by this matrix operation. So, let us carry out this matrix representation when you operate on pure states, on pure qubits 0 and 1 represented by the matrices 1 and 0. So, when you operate on the qubit 0, you get a superposition of 0 and 1. So, again you have sort of mixed the pure states, and you have converted a pure state into a superposition state or into a mixed state. You do the same whether the pure state was 0 or 1. Okay, but you get different superpositions which are orthogonal to each other. But then if you do it twice, you get the unit operator. Okay, so this is really amazing. So, you randomize it, you generate superpositions, and then you put it through a Hadamard gate and you can get pure gates, pure qubits. Okay. So, this is what the Hadamard gate does to a quantum qubit. it generates superpositions depending on whatever the coefficients alpha 0 and alpha 1 are. These coefficients of course can be 1 over root 2 if they come in equal proportions with respect to the probabilities of occurrence, and that is when they provide great advantage. So, it converts the mixed state into a pure state when you operate twice, but when you operate only once, it converts a pure state into a mixed state. And depending on what kind of quantum result you want to achieve, you determine what kind of a gate you want to use and how many times you want to use it, right. Using it twice has a different result. So, here is another gate which is represented by these phase type terms in the coefficients, right, of the matrix. And let us ask what effect this matrix will have on a quantum qubit, and that qubit can be a superposition of 0 and 1 with a plus sign or a minus sign, and depending on the plus sign and the minus sign you get 1 over root 2 and then you have e to the I theta and plus or minus e to the I phi. Okay? So, one might think that okay, what is the big deal, because you have got these phase factors, and then when you take the probability of finding a state in an eigenstate, you have to get the modulus square of the coefficient, right. So, you have to take that coefficient and multiply it by its complex conjugate, and the e to the I theta will multiply e to the minus I theta, and you would not have got any help from this operation. So, it seems that you will not be able to distinguish between this from what you started out with, but then look at this amazing thing that quantum theory lets you do. So, to illustrate this, we will take a special case, we will take theta equal to 0, phi equal to pi. So, now the operation of the G gate gives you 1 over root 2 and then minus or plus 1 over root 2, okay, because phi is equal to pi. So, you get minus or plus instead of plus or minus e to the I phi, okay. And now on this result, if you now subject this, you pass this qubit through a Hadamard gate, okay. So, now operate on this by the Hadamard matrix. So, the Hadamard matrix is 1 over root 2 1 1 1 minus 1, and what you have got is either pure 0 or pure 1. So, the intermediate state, it seemed that you just had to pick phase factor and it would not really matter, but essentially what the subsequent operation by Hadamard gate allows you to do is to determine if that state was either a 0 or 1. So, this basis is called as a computational basis. Okay. Any basis, any linear superposition of this will be an equivalent basis, and in usual quantum mechanics it would be perfectly acceptable to use any linearly independent complete set of bases. Okay. But in quantum computing, this is a preferred choice and it is called as the computational basis. And we have seen what the Hadamard gate does to this basis, and you get superpositions. You can use the superpositions also as a basis set, okay, because it also gives you a linearly independent basis. It is complete, it is orthogonal, right, it is normalized. So, it is a perfectly acceptable basis, and this basis is called as a Hadamard basis. Okay. So, you can use the Hadamard basis or the computational basis. So, these two are rather popular choices. The computational basis is what is most often used. Then there is the phase gate, which gives you e to the I pi by 2 factor, and all of these quantum gates are then essentially represented by 2 by 2 matrices. Okay, and these can actually be implemented using physical devices, because at the end of the day you need to use your logic and build circuits and devices. Okay? So, for that certain physical devices are used, and I will talk about it in the next class. I will take up the case of the nuclear magnetic resonance phenomenon. We will use the spin half quantum systems, and these have actually been used to build quantum gates. The NOT gate has been built, the square root of NOT gate, the control NOT gate, and we will be discussing some of these applications. So, that is where I will start in the next class. If there is any question, I can take it here.
So, what is the difference between the square root gate and coin flip gate? I am confused between them. Like, are they same or are they different?
The quantum coin flip gate is the quantum square root gate, the square root of NOT gate.
Okay.
Not the classical.
Okay.
Yeah. So, there is a classical coin flip gate which will give you the half-half, okay, and then there is the quantum coin flip gate. So, the quantum coin flip gate is the one which gives you the square root of NOT gate. Yeah, but then there is a minus sign to remember. Yeah.
And so we talked that it generates randomized number. Like, I'm still confused. How does it do it?
Yeah, the result of this is random.
Then
okay, when you flip a coin, okay, there is an equal chance of getting opposite results. That is what you exploit, means the actual building of a randomizer is more complex, but it is based on this principle. So, we are first illustrating the principles. Essentially, it is based on the idea that you begin with something that is known. Okay, when you toss a coin, you know that it is the heads which is up, or you know if the tail is up. So, the initial state you know, but you do not know what you are going to get. The chance of getting just the opposites are equal.
Even the Hadamard gate does the similar thing, right? It generates 1 by root 2 0 plus 1 by root 2 1.
Yeah, so the Hadamard gate does many fantastic things in quantum circuits. So, I have shown you some of the things, we are going to use it some more. So, you will see the applications in the next class or in the next 2 or 3 classes. Yeah.
So, in the introduction, you have mentioned like quantum logic gates are reversible.
Yeah.
So, what is meant by reversible here?
But you can perform an operation on the result by the inverse of this matrix and recover the previous matrix that you started out with, because these are unitary transformations. Yeah. So, physical processes in nature are reversible, but then at a thermodynamic level something else happens. Yeah. But each individual process essentially is reversible.